In this video, I'm going to talk about TCP reliability. There are two mechanisms, the TCP retransmission and fast retransmission. Now let's start with a review, simple review about TCP header, TCP protocol, mainly TCP header. We know that TCP protocol is a reliable protocol in the sense that if any information is lost, it's going to be retransmitted. Also, TCP is connection oriented. It means that two computers communicate using TCP protocol at transport layer. They have first to establish TCP connection. Once this TCP connection is established, then they will use it to exchange their information. At the end, this TCP connection will be dropped. Now let's have a look at this TCP header. We have a source port which is stored in 2 bytes. Destination port here is 2 bytes length field. The next field is sequence number 4 bytes, acknowledgement number 4 bytes, data offset, which contains the length of TCP header because the length of TCP header can expand due to options or optional information that are which can be inserted in the TCP header. So we have to keep track about the length of the header of every TCP segment. Now this is reserved field, which is out of the scope. The CWR and the ECE, these 2 bits are used for other things. These 6 bits here constitute the flags field. So these are the fields which are going to manage the establishment of the connection or indicate actually the status of the TCP connection. Now the next field is window size. It's used for flow control. This field here is a checksum, 2 bytes long field. It's used to store checksum, and checksum in TCP is mandatory. And finally we have the urgent pointer, which needs 2 bytes, which is a 2 byte long field. Now if we look at the TCP header without options, we find that the TCP header length is 20 bytes. So this one here is 4 bytes, 2 bytes for source port, 2 bytes for destination port. So this makes 4 bytes, sequence number 4 bytes, so 8 bytes plus 4 bytes of acknowledgement number, 12 bytes plus 4 bytes, here 16 bytes plus the last 4 bytes, 20 bytes. So the minimum length of TCP header is 20 bytes. Now let's review the sequence numbering. So we know that TCP is a byte stream protocol in the sense that the sequence number that you will find in the header of TCP indicate the sequence number of the very first bytes in the payload. Now if we have, for example, this number of bytes in the payload, each one of them will have its own sequence number. So for example, here we read in the TCP header sequence number equal to 20, which means that the very first byte in the payload has sequence number 20, and then the next byte 21, 22, and so on until the last byte. Of course, we cannot represent the sequence number of each byte. That's why only the sequence number of the first byte is represented in the TCP header. In the acknowledgement, here we read 33. That means that you have to take sequence number 20 plus the length of the TCP payload, which is 13 bytes. So you count here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 bytes. So 20 plus 13 is equal to 33. So when the destination or the receiver sends a TCP segment with acknowledgement equal to 33, it means that it received sequence number 32. And this is true. So this is sequence number 20, 21, 22, and so on until 32. So now the receiver is telling the sender that I received up to 32. Now the next TCP segment to be expected that I expect to receive from you should have sequence number 33. So this is the way TCP protocol is going to track down every TCP segment, and in case one TCP segment is lost, it's going to be detected. So now the next TCP segment, which is sent from the server side, has sequence number 33, and it is exactly as the one which is expected by the receiver, and the receiver knows exactly what it should receive in terms of sequence number. Now let's go to TCP acknowledgement. We know that whenever the client, the TCP client, establish connection with the TCP server, so it's going to exchange data. So it will send the first TCP segment, as you notice here, sequence number 1, and the length of the payload is 5 bytes. Now as soon as the client, TCP client, sends this TCP segment, it will start a timer for this TCP segment. So the timer This is the period during which the TCP client expects to receive acknowledgement from the server. Now the server, TCP server, upon receiving this TCP segment from the client, is going to reply by sending acknowledgement. Look here, acknowledgement is equal to 6. Take sequence number 1 plus length of the data 5. 1 plus 5 is equal to 6. So now the TCP server is acknowledging receiving this TCP segment. So it says, I received up to 5. Now the next TCP segment that I expect to receive from you should have sequence number 6. And this is what will happen. So the TCP client is going to send the next TCP segment with sequence number equal to 6, and the length of the payload equals to 10 bytes. Now the TCP server received this TCP segment and acknowledge it by sending TCP segment with acknowledgement equal to 16. So 6 plus 10 is equal to 16, which means that the next TCP segment which is expected to be received is has sequence number equal to 16. So in this case, 16 plus length of payload 15 is equal to 31. This is what's going to be sent as part of the acknowledgement. Now you notice for every TCP segment which is sent by the client to the server, it has its started timer. During this period, the client expects to receive the acknowledgement. Also, this is true also for every computer which is sending TCP segment. It is true, it applies for TCP client as well as for TCP server. Now look what happens. Now in this scenario, TCP client is sending the first TCP segment to the server. Now the server receives it and acknowledges it. Now as long as the acknowledgement is received within this the time period, before the timer times out, it's okay. Now the TCP client is going to send the second TCP segment which is expected to be received by the TCP server. TCP server now is sending the acknowledgement, but for some reason this acknowledgement is lost. So the client does not receive acknowledgement. It will time out. Okay, so this period it will expire, and then it's going to retransmit again the TCP segment which has not been acknowledged. So you notice here in TCP retransmission, the TCP segment has been received by the other end, here the TCP server. However, what is missing is the acknowledgement. So the acknowledgement is lost due to some reason. Either the acknowledgement is lost, or the acknowledgement is caught in a queue. There is congestion, so the acknowledgement cannot make it before the client timeout for this specific TCP segment. So the client does not see the acknowledgement and it times out, so it will retransmit the TCP segment to the TCP server. Now let's look at the second case here. We have a TCP client send the TCP segment to the TCP server, and then it starts a timer. Now it sends the second TCP segment to the TCP server. Again, it will start a timer related to the second TCP segment. Now the acknowledgement for the first TCP segment is sent by the TCP server to the client. However, it is not received on time. Maybe there is congestion which prevented this TCP segment to be received on time. So this TCP segment does not reach the client before it times out. So here the client thinks that this TCP segment was not received. Now what it will do is going to retransmit it. It's going to retransmit this TCP segment which has not been acknowledged. However, after some time it's going to receive the acknowledgement for the second TCP segment. So if you count sequence number plus 10, sequence number plus the length of the payload, 6 plus 10 is equal to 16. So here the client receives the acknowledgement for the second TCP segment. Now once the client receives a TCP segment for the second TCP segment using the cumulative acknowledgement, the client understands that the first TCP segment was received. Even though it has retransmitted, it's too late, it has already retransmitted this TCP segment, sequence number 1. However, since it receives acknowledgement 16, using our knowledge about cumulative acknowledgement, so it knows that the first TCP segment has been received at the other end. How the TCP server now will react when it receives duplicate TCP segment with respect to the first one is going to send acknowledgement. But look here, the acknowledgement is not going to be 6, it's going to be 16. Now the TCP server is informing the client, I receive it up to 15, which means that I received the sequence number 1 and I received the second TCP segment which starts with sequence number 16. So like this we see a good example about cumulative acknowledgement, but also this is a second case or second example about when retransmission can happen. Now the third case of retransmission here, we have the TCP client which is going to send a TCP segment with sequence number 1 and payload length equal to 5. It will send it back to back with another TCP segment, sequence number 6, payload length 10 bytes. Now once this TCP segment is received at TCP server side, TCP server will acknowledge the sequence number 1. It will send acknowledgement number 6, and then it receives the second TCP segment and it sends the acknowledgement for the second TCP segment, which is 16. Now for some reason the first acknowledgement is lost, or it gets caught behind some congestion, heavy queues, etc. So the second acknowledgement makes it to the client. When the client receives the second acknowledgement, then everything is fine. It understands that all the 2 TCP segments have been received. Again, this is related to cumulative acknowledgement. So if I receive acknowledgement 15, what do I understand from this is that TCP segments up to bytes up to 15 have been received, starting from 1, 2, 3, 4, 5, 6, 7, 8, 9 until 15, even though the client did not receive acknowledgement 6, which is specific acknowledgement to the first TCP segment. So these are 3 cases of TCP retransmission. So to wrap up, we say that in TCP retransmission, a TCP segment is received at the other end. However, what is missing here is the acknowledgement for that TCP segment. So whenever the acknowledgement for that particular TCP segment which is received at the other end is lost, when that acknowledgement is lost, then we have a scenario of TCP retransmission. Now we have another case of figure here, which is a TCP Fast-retransmission, which is a different situation. Here the client is going to send a TCP segment to the server. TCP server, when receiving this TCP segment, it will acknowledge it. It will send acknowledgement number 6. That's fine. Now the TCP client will send the second TCP segment. Now for some reason this second TCP segment is lost. It cannot make it due to some reason. Now the TCP client will send a third TCP segment whose sequence number is 16. Of course, the TCP server did not receive the expected TCP segment. So I did not receive any TCP segment whose sequence number is equal to 6. Instead, it received a sequence number, a TCP segment whose sequence number is equal to 16. So the TCP segment, the TCP server is expecting TCP segment with sequence number 6. Instead, it receives a TCP segment with sequence number equals to 16. So where is this sequence number 6? So that's why here TCP server is going to insist and send the acknowledgement to TCP client, and it keeps in this acknowledgement its request to receive sequence number 6, or TCP segment with sequence number 6. Now the TCP client will receive this acknowledgement the first time. Maybe the second TCP segment was behind the congestion, was caught in a congestion. Now it's going to receive a second TCP segment acknowledgement from the TCP server, and the second acknowledgement is always telling that I'm expecting sequence number 6, TCP segment with sequence number 6. So the client will receive it, and then the TCP server will send a third acknowledgement which is equal to 6, which means that the TCP server is sending 3 duplicate acknowledgement for the expected TCP segment, which should have sequence number equal to 6. Once the client receives this 3 duplicate acknowledgement plus because it already received the original one, but these are duplicate with respect to the original acknowledgement. At that moment, it's going to fast retransmit the TCP segment, which is here, which is expected to be received by the TCP server. So it's going to fast retransmit it. Now, in fast retransmission, you don't have to wait until the client or the timer on the client side times out, like this is the case for TCP retransmission. Now, the TCP client, once it receives the 3 duplicate acknowledgement, is going to fast retransmit before the timer expires. That's why we call it fast retransmission. Now we have to be very careful here. Here we talk about 3 duplicates. Nowadays, it's possible to change this number through operating system, through the protocol, the TCP IP protocol stack implemented in the operating system. Some operating system actually have their protocol stack use 2 duplicates. So whenever it receives 2 duplicate acknowledgement, then it will fast retransmit. Now this number can be controlled. So through the operating system, you can control the number of duplicate acknowledgement that the server can send to the client in order for the client to fast retransmit.